Cool. So, today we're gonna reintroduce ourselves to Postgres, which is a type of relational database. And we're also going to talk about data modeling. You'll also hear me use the term schema design, which is basically designing a database. And some of this will be review because Francisco took you through a healthy chunk of this in the full stack week. So some of this will be a review, some of this will be a refresher, some of this will reinforce some concepts, and some of this we might not see too much new technical stuff today, but we'll definitely see like a new technique for designing databases. And there's a couple really useful tools that we'll be using that we'll be seeing later, but there's a couple really, really nice tools for helping you like visualize your data schemas that I'll be talking about. And these are all linked to in the course. So just to give a kind of big picture overview of the week and today, really like stepping back a little bit. Like databases are sort of the heart of your system. There's a couple different kinds of relational databases. Postgres is only one. MySQL, which many of you may have heard of, and MariaDB are other relational databases. And I'm going to talk in a little bit about what is a relational database specifically. And I'm going to talk a little bit about, I hope I got this acronym right, but SQL, the structured query language, which we've seen, and we're going to talk about it a bit more. So what is the goal of this module? Once we get to Django, you'll see that Django actually does a lot of work for us. You may have gotten a little bit of a preview of this in the full stack week, where there's something called an object relationship mapper or models, where we don't have to directly write our SQL. This sometimes will be true in your career, but not always. SQL has been around since really the 50s or 60s. It's kind of like a shark, like one of these creatures that just nature has sort of perfected. And, you know, it's far from perfect, but it's not going anywhere. And so the goal this week is to get really comfortable just with SQL and Postgres specifically, because it's super useful so that you can understand what these more powerful tools are doing. And also because in your career, you may find that you need to write some SQL to run some analytics queries or something. Like database design and writing queries can get quite complicated. Like at bigger companies, they might have, you know, someone who is a database admin. So there's like a whole career path that goes deep into that. But this is really sort of like the programmer's fundamentals. And today we're going to be sort of talking about what is a relational database, how do I design one. Tomorrow we're going to dig into writing SQL queries more and working really with CSV files, getting data in, getting data out. Wednesday we're going to spend more time looking at kind of the relationships that you can make between tables in a relational database and just some of the tools that Postgres gives you. Thursday, we actually have a workshop that was designed by some volunteers, which is really awesome. And unfortunately, they weren't able to run it this time, but we have pretty much all the pieces. So our Thursday workshop will sort of be an all-day code-along affair where we will like go over everything from the past 3 days plus a bit more. And then on Friday, we'll do a review and we've got our assessment. So that's sort of the plan for the week. And so just to dive in, the first bit of what I'm going to talk about here, and actually before I dive in, do folks have any questions? Okay, cool. So this is really the plan for today. a good amount of what I'm going to talk about today is more background contextual knowledge. There's one bit in particular, this acronym ACID, that I'll point out when we get to it, that sometimes shows up in technical interviews. But other than that, if when I'm talking about sort of like conceptual stuff, please take notes if it helps you learn, but most of this stuff is more for your own context and understanding. And as always, it's really the hard skills that the assessment covers. So a lot of this, I think, is sort of review in a sense, but just to kind of kick it off, like, what is a database? Why do we care? I think the most important thing to touch on here, we've all installed Postgres, and we've got Postgres and we've got pSQL, and they're two separate programs. And the Postgres program, we'll often call that a database server or a database engine. In like a production web application, there would be, a virtual server in the cloud just running Postgres. And these database engines are designed to handle like thousands of connections per second. And so that's why we'll talk about the Postgres engine. And there's really powerful things that databases give us. Writing data, right? Create, read, update, destroy, or CRUD, which is an acronym that you'll come back to. Reading our data is part of CRUD. Organizing our data. And with relational databases, the table is the main metaphor that they use. Persisting data. Databases make sure that like stuff doesn't accidentally get deleted, that things are easy to back up. Access control. You can create multiple databases in Postgres and control who has access to what. As you've discovered, you have to make a user account, right, to interact with Postgres. And data integrity, to make sure that our data doesn't get messed up. And database programs do this extremely efficiently. And so just to give a little context, here's an imaginary retail store. And can you all see this diagram okay? Cool, awesome. How is my internet connection, by the way? So. Okay, let me see if I can fix this real quick. Okay, so we were looking at this diagram. This is jumping ahead a little bit because this is a whole web application architecture where we've got the cloud, something like Amazon Web Services, and we have some API servers, which you got the preview of with Flask in the full stack week, and that will be writing in Django soon. We've got our Postgres database. We have load balancers, which is just a fancy word for a server that distributes traffic between other servers. And then we have some users. And so in this scenario, we've got a retail store, and they have two different databases, really, and two different applications. They've got inventory that they want their store employees and managers to be able to interact with. And they've got payroll and accounting, and they want the accountant to interact with that. They don't really want the store manager and the employees to be able to get at the accounting information. And so as you can see here, like you can create multiple databases in Postgres, as is done here, and control which programs have access to them. So these accounting API servers can only access the accounting database, and these inventory API servers can only access the inventory database. And that means that like there's no way, for the store manager to look at payroll or accounting information that's stored in the other system. And not every big like company architecture is like this these days. But this was for a very long time the classic approach where like you had one database that was the hub of everything. For various reasons, often this is like these days you might have separate databases for each of these applications, but you'll still see this approach a lot. I just want to check in to see if folks have any questions, and if just that very high level overview sort of makes sense of what's going on here. and one of the things that like a database server like Postgres provides. Cool. Yeah, Andrew, a load balancer, this is getting ahead of things a little bit, but like if we are Amazon and we have a huge amount of traffic, you know, millions of requests per minute, what we'll often want to do is we will have multiple web servers. And then when I want to go to Amazon.com, when I make that request, my browser, the first thing it talks to is actually a server called a load balancer. And all it does is distribute traffic. Like you could imagine, I request something from Amazon. And so like my request goes to this first one here. And then Andrew, your request, the load balancer sends to this one here. And then Anthony, yours goes to here. And then Fu, yours goes to here. So all it's doing is distributing traffic amongst servers. And that's one way of scaling up. But that's really outside of scope for this week. I just wanted to give a little bit of depth to the diagram here. Great question. So the most important piece of this is actually the programmer up in the corner here. And this is us. And we're on our laptop and we're running pSQL on our laptop. And pSQL is a client program. We can connect to this Postgres database server in the cloud and interact with it just like we have. So in class, we're always running Postgres on our own laptops. But often for like a sort of real world or production architecture, your database server is somewhere else. And we talk to it with pSQL and we can access everything, right? All of the databases. And that's also why databases offer like auditing and logging tools, and why companies do a lot of auditing and logging too, because they don't want the programmer to, you know, be able to like do an office space and like steal like fractions of cents from accounts or something like that. And do folks have any questions kind of about that before I move on? Cool. So this is just sort of a review of what I just talked about. So now let's talk a bit about relational databases specifically. There's a bunch of different kinds of databases. Like a common alternative these days to a relational database is what's called a NoSQL database or a document database, where instead of tables and rows, you basically, they call them documents, and it looks an awful lot like JSON. So this is not stuff that you need to know for the assessment. I just want to show a counterpoint so we can understand some of the differences. So a NoSQL database like MongoDB does not have tables. You do not use SQL to query it. You can have relationships with documents, but it's different. And a lot of the structure that relational databases give us, some NoSQL databases don't. But as I'll talk about a bit later, there's a lot of like, there are like hybrid databases as well. And so just going through the questions in the chat. Blockchain is kind of its own thing, Brian. I'm not sure I would call that a database. I honestly would have to look up blockchain a bit more. It's like a whole thing. My understanding is blockchain can be good for sort of like sort of a ledger of what has happened and tracking that and distributing that. And so some financial institutions are interested in that. But that's sort of its own thing. And the whole question of like, do we need to have a decentralized database or not is a whole ball of wax that just has a lot of different things. But in essence, I would not think of blockchain and databases in the same category. Though you can do some similar things with blockchain. And Josh, that's correct. We're going to have our Postgres assessment on Friday. So relational databases, unlike, have been around for quite a while, and they give us tables and columns and rows. And this should probably sound pretty familiar to you guys, right? We organize our data into tables such as customers and purchases. And, spreadsheets show this metaphor really well. The tables have columns, first name, last name, item, quantity, and then the data is in rows. And so under the hood, this is how relational databases store stuff. We can also add constraints to our tables, and we can make rules. For example, we could say this email row in the customers table cannot be null. And those kinds of constraints are actually really powerful because we can design our data like we never want a customer without an email. And that's one of the advantages of a relational database is often they're just much more robust in terms of like rules. So the other thing that relational databases do really well is relationships between tables. And we do this with something called a primary key and a foreign key. And can someone just maybe recap for me, like what, if you remember from the full stack week or from looking at this before, what are primary keys and foreign keys, and what do they do in a relational database?
Primary key would be a unique value that would be initiated every time a new thing is inserted into a table, and a foreign key would be a linked key from another table.
Yeah, exactly. A primary key, we almost always, whenever we create a table in a relational database, want to add a primary key, and each row gets a primary key. And for customers, the primary key is ID. For purchases, the primary key is also ID. And that is normally what you want to name your primary key because it's customers.id or purchases.id. And it uniquely identifies each row in that table. And then, just like you were saying, Brian, the cool thing is now that I have something to uniquely identify the customers table, over here in purchases, I can have this column customer ID, and that holds an ID. This one is 2 of the second row of data in our customers table, and this one is 1 in the first. And so customer ID here is what's called a foreign key, because it's a primary key of something else, of a foreign table. And you can actually define these relationships when you define your tables. And that's how you can tell the database how our data relates to each other. And so I drew this with one of these great programs up here. I think it was Draw SQL, but they're all pretty great. You can import an SQL file. You can create the diagram. There's a lot of ways to do it. And you can see this relationship here where the primary key of the customers table is used as a foreign key here on the purchases table. The other thing to note about this diagram is this little line has these 3 lines at the end of it. These are called crow's feet. And I'll talk about it a bit later, but this represents what's called a one-to-many relationship between the tables. Each purchase can only belong to one customer, right? 2 people can't have the same invoice order from Amazon, but one customer can make a whole bunch of purchases. So we could have here in this purchase table, maybe Bob has bought a whole bunch of things. And when we design our data schema or our data model, we decide about these relationships between tables as well. And let me just pause here and see if folks have any questions. And is this pretty familiar? I'm guessing that this is, that we've talked a little bit about this in the full stack week and that you all have seen this before. Can I just get a sanity check? Is this ringing bells to people? Is this new information? Like what's our sort of familiarity level with this thus far?
I know we covered it to a point. Like we mentioned foreign keys and primary keys, but we
Yeah.
didn't go in depth at all.
Okay, awesome. Megan, thank you. And Frank, thank you for the thumbs up, and Brian and Derek as well. Okay, perfect. That is super helpful because I knew we talked about it a little bit, but I wasn't sure how much. So primary keys and foreign keys are probably the most important thing with Postgres and relational databases. And just to illustrate really quickly, there's a couple of these tools here. I'll use QuickDB. Oh, this is something else. We'll get rid of all this stuff if it lets me. Oh, login or well, let's use the other one because I'm lazy. So these visualization tools are great and are going to be a big part of kind of the class. And I think maybe I'll come back to it in a bit because it's loading, which is a little annoying. And I apologize that it seems like my internet is giving me trouble. They're pretty intuitive once you start working with them. The main thing is not to use them as a shortcut to generate SQL. Use them to help design, but get that muscle memory building of writing out the SQL for your databases yourself. And a little bit later in the lesson, I'll come back to them and build stuff. Oh, and here we've got this diagram, and you can kind of see here, like you can define your columns. And so here, if I wanted to add a column, I could go ahead and do that. And I don't know, we'll just call this date and make it timestamp. And then you can actually import an SQL file into here to visualize a whole diagram. And you just sort of drag between the two to make connections. And you can see here that this is the primary key. And that over here is a primary key as well. And I don't know if we explicitly told it that. I think, yeah, there might be a way to specify a foreign key, but mainly it knows with this sort of the drawing the connection here. The main thing to know is that each table can only have one primary key, right? Because that's what uniquely identifies each row. You can actually have multiple foreign keys, and we'll see that later. There's a technique called a join table for many-to-many relationships that has multiple foreign keys. So this basic concept is super important. So I do want to check in to see if people have any questions or would like me to review a bit about this basic idea of we can create tables, we can give tables primary keys, and then on my purchases table, I can reference the customer's primary key, and that's a foreign key, and that's how I can define these relationships. Cool. Awesome. And we're going to get some practice with this in a bit. So we use the structured query language, or SQL, to do almost everything with our relational databases. It's extremely powerful. And there's actually a lot of sort of interesting stuff behind it. And there's a whole there's a whole lot more to learn. There's something called relational algebra that we don't really have to worry about. The most important pieces here is that with SQL, we can create these tables, and I'm gonna demo all this in a little bit. We can create tables, we can modify tables, and all of our tables and their relationships in like one database, like is what we call the data schema. Our tables, their columns and constraints and relationships. We can use SQL to insert data. We can use it to delete tables or delete whole databases. We can use it to delete data. We can use it to specify these relationships. You can even use SQL to like create users and manage permissions and stuff. Excuse me. So let me go ahead and just demo a little bit of this. And give me a moment here just to get my screen set up. And if you want to code along, you can, but that is not really the goal right now. And so I am going to move at a little bit of a quicker pace, but please do, I'll check in, but please do ask questions as well as we go. Because the goal here this morning is really understanding. I've got an exercise for you all to do. So we'll break in about 30 minutes, and then there'll be a group exercise and then a bit more lecture. So there'll be some hands-on time a bit later. So we're going to create this simple retail store database. And so the first thing I'm going to do is log into Postgres. And we'll learn in a little bit how to write in SQL files and execute them. But we can also run SQL right in pSQL. I remember that pSQL is our client program talking to the Postgres engine itself. If I just do a little, let's see, maybe is it L /L, the / indicates like a pSQL command that lists all the different databases in here, I believe. And there's actually, if you guys notice, can you see the terminal okay? Is the font size good? Cool. There's actually a database in here named Postgres. As some of you may recall from InstallFest, this is the default database created when we install Postgres. And this is the database that Postgres uses to manage all the other databases in the user accounts. So we could actually log in here and look at that stuff, and it can kind of be cool to connect to it and see what's going on, but you don't want to modify it directly. That is going to cause problems. So the way we connect to a database is with /C. And actually the retail store database already exists. So let me go ahead and delete it. And let me see if I have this command correct. Yep. So pSQL has told us that it's dropped the database. And if I go in, it's gone. Now, if I want to connect to it, I use /C. And I wanted to demonstrate this error. There's a lot of junk in this message that we don't have to care about. Telling us how pSQL is connecting to the server. It's this little bit here after fatal that matters. And so this error is telling me that the database does not exist. By the way, the uppercase for SQL commands is just a convention for readability. So to save like my fingers for typing, I'm going to, when I'm typing commands out, just use lowercase. And now that database has been created, I can hit the up arrow in pSQL to go back to connect, and let's connect to the retail store. And we are now connected to the retail store. And there's also a nifty command connection info that will just print out my user, what database I'm connected to, and I think this is the port that Postgres is running on. So let's go ahead and create these tables. And I think I am going to actually write some SQL here, and then run it from pSQL, because to be honest, pSQL is great for like queries and typing little commands in there. But like if I have to type like multiple lines, I like to do it in a file. So let me show you all what this looks like. And let me quickly navigate to where I want to be. So let me make a file named retail store. We're gonna call this init retail store schema.sql. And what I've done, by the way, is I opened up two terminals so I can have pSQL here, but I can also have the terminal, the command line to type stuff. So let's create our customers table. And there's a couple ways to write comments in SQL. For a one-line comment, you do 2 dashes. Our customers table is going to have an ID. It's going to have a first name. And it's going to have a last name. And it's going to have an email. And these are our columns. Remember, if we kind of go back up here, or to go back up here. So we're defining the columns for this table. With relational databases, columns have to have a type. Like you can't put whatever you want in a column. It has to have a certain kind of data. So the ID is our primary key. And this is good to note down, but this is also documented in the lesson, and you'll see this a bunch of places. I'm going to go ahead and type out the fields for each of these and then talk very briefly about what they mean. So for a primary key, you can see right off the bat, we can actually just tell Postgres, hey, this column is a primary key. This special keyword serial up front, this tells Postgres basically to auto increment. We don't have to create these primary key values. Like think serial in terms of like increasing one after the other, as in 1, 2, 3, 4, 5. So this creates an integer column for us that Postgres will create new values for, and it will do that work for us. And there are other ways to define primary keys, but this is a pretty common way in Postgres, and it's probably how you all will define your primary keys. Varchar stands for variable character, I believe, or varying characters. Think alphanumeric like ABC 1, 2, 3. And we can also give it a limit to how many characters are allowed. And so basically a text field for first name, last name, and email. The maximum length that you can give a field is 255 characters. So when learning this, we'll often talk about like it's good to think about how many characters first name, last name, email should have. A couple considerations in the real world, though. One, you'll be surprised how often someone says, well, first name only needs 10 characters because who's got a first name longer than 10 characters? And then 2 years from now, the company expands into a new market in a different country where first names are really long. And all of a sudden, this is really hard to change. So in some ways, it's better to go bigger rather than smaller. The other real world consideration is Postgres specifically. I can't speak for MySQL or other relational databases here. If you kind of read their documentation, they say, hey, Postgres will actually optimize how long these should be. You don't get like performance or savings benefits by specifying it. So don't. So Postgres actually recommends just to say varchar. There's another field called text that's extremely similar. This is meant for like whole paragraphs. But what I would recommend is for text fields, just put varchar. Don't worry about the number. And then later on, if you find out you need something more, you can add it. And the last thing I am going to add in here is a constraint that our email address should not be null. And SQL statements end with a semicolon, right? So you could put all of this on one line if you wanted. I probably don't want that comma there, but it's just easier to read on multiple lines. And so we've got this command, create table, the name of the table, and then the details of the table that we're going to create in parentheses. And this is a common syntax that you'll see with SQL queries. And let's go ahead and create the purchases table. And actually, could someone just walk me through this? Like, what are the columns that we want here and what should their values be?
Do we want to do an ID?
Yep.
Then maybe item name.
Yep. Item. I'll just put item.
And then price.
Price. Yep. I'm going to put cost. What else?
Quantity and customer ID.
Yep. And I know that, and thank you guys. I know that I also kind of have this in the doc for today. And what is this? What is the customer ID column again? And what type is it going to be?
Foreign key.
Yeah, a foreign key, and describe to me what customer ID is doing. It's a foreign key connecting what to what?
The ID in the customers table to the purchases.
Yeah, exactly. And so the way in Postgres that we define a foreign key is first we tell Postgres what type it is. And it's almost always an integer. And then we use this special keyword references and we give it the name of our table. And tables should always be named plural, by the way. And then we give it the column on that table that's the primary key. So customer ID here on our purchases table is a foreign key. It's an integer because this is an integer and it references customer's ID. And now Postgres knows about this relationship. I'm going to go ahead and make this our primary key. And I'm going to go ahead and make this just a string essentially. And quantity, the amount of stuff we purchase, is going to be an integer. And cost, I'm just going to make that an integer as well for now. And now we've got our two tables. And by the way, the other way to comment in Postgres is with the /*. Like so. But actually, I think in the interest of keeping everything readable, I'll just do it that way so that we can see pretty much everything here. And I need to put a semicolon at the end of this. And so now we've got these two tables that we've created, and we've kind of walked through what's going on. We've got a bunch of columns. The columns have types. Each table has a primary key, and our purchases table references the customers table. Real quick, why do we even want separate customers and purchases tables? And there are a bunch of different reasons. So there's not really a wrong answer here, but what are some people's thoughts about that?
Abstraction, like Matt illustrated this morning.
Yeah, abstraction. There's also the question of if once we start to get like hundreds of thousands of customers and purchases, saving data. If I had, you know, customer name, customer email, customer address on each purchase thing, this is a lot of data that's going to be repeated if the same customer buys a whole bunch of things. So by breaking stuff up into separate tables, we're not storing the same information in multiple places, which could be a real problem. Like maybe the customer's email address changes, though that presents its own issues. But this not duplicating data is a big deal in like database design. And there's this whole thing called normalization, which is really out of scope of what we're looking at this week, but essentially is saying like, hey, don't repeat data and like have each table do one specific thing. Like you might even end up, instead of an address here, you might have a customer address table because maybe there are two customers with the same address, right? Maybe two people who live in the same house have Amazon accounts. But the basic principle here is kind of don't repeat data. Though sometimes in the real world you might want to and kind of have tables for specific things. And that's what we'll get a lot of practice doing this week. So we've gone ahead and written our SQL. Any questions kind of about this SQL and this data schema before we actually, you know, create the database? Or anything that folks would like me to go over? Eric, yes, sir.
Yeah, I just had a quick question. In the purchases table that you created, what is the difference between using the references keyword and the foreign key keyword for the customer
That's a
ID?
great question. I am not 100%, but I'm like 75% sure that they are synonyms and do the same thing. Let's see what the internet says. I should have just asked ChatGPT, really. Oh, it looks like foreign key might be a little stricter. I see. Okay, actually, I did not know that. This is a little into the weeds, but I guess Postgres has a foreign key command as well, and you have to type it like this, where you say foreign key references, and then this other key. And I guess you can only use it to point to a primary key of another table. If we just use references, we can point it to something that's not a primary key, which is a little more advanced. We won't really see that this week. But as long as we're just pointing to primary keys on another table, both of these will do the same thing for us.
Thank you.
Yeah, that's a great question. The Postgres documentation is actually very good. In fact, we can take a quick look at it now. Though it can It's a little dense, but it's quite good as it goes. And they have actually I've assigned a little bit of reading and exercises from it for today. So somewhere in here, they have a whole breakdown. I'm not gonna try and find it. Actually, let's see here. Yeah, they have like a whole section where they go very much in depth to kind of like describe things. And they would probably go into the exact explanation of the difference here. For our purposes, they're interchangeable. Because we're almost always going to have our foreign key be some other table's primary key. Yeah, that's a really good question. There's a couple other ways to do things in Postgres. Like I think you might be able to do int, that's short for integer. There's a couple other aliases. What other questions do people have? And I should have the participants channel up, but if I miss a hand at some point, please just speak up. Okay, cool. Well, we've written this SQL. Let's run it. So let me pop back over to pSQL here. And I'm going to quit real quick because I want to show us our directory structure. So right now, I'm in the directory that has my SQL file with the code with the SQL that I want to run. So from the directory where my SQL is, I'm going to log into pSQL. I'm going to connect to the retail store. And there is tab completion here, by the way, which is great. And we can use the command /I believe, and this will let us run an SQL file. And I believe we can give it, there is I and IR. I think you can actually give a relative path to both. And that is what I recommend is we are going to pass this command the relative path of where our file is, and we are going to run it. And let me make sure I am doing this correctly. So I do have to type this out. Oh no, I don't actually. There is tab completion, which is amazing. So remember that // is a relative path. And so that's why it's like if you ran pSQL from a different directory other than where the file is, you'd have to give the path to where it was. And you can do absolute paths here too. But I think this is going to be the easiest way to do it. Just run pSQL from the directory that your SQL files live in, and then you can just use // for a relative path. And lo and behold, it says we've created some tables. Let's see what we got. So I can use the command, I believe it's /D, and this gives us this list of relationships. And note this sequence thing here. So this is kind of how Postgres does primary keys under the hood. D is short for describe. I can also do DT to just show us the tables. And we can see the two tables that we created. And if I do /D and then customers, I can see a whole lot of information about that table. And you will want to use this /D Postgres command, but it's also in the lesson. So you'll have it as a reference. And we can see here our columns, and we can see the type of each column, varchar, right, varying character. Note that the primary key ID is an integer type. Postgres, because we said all this stuff about serial primary key, Postgres has decided it cannot be null and done that for us. This not null constraint we added right here, remember? And this is just some fancy stuff of Postgres saying, I'm going to generate the integer values for this ID. And if we take a quick look at the purchases table, we'll see something very similar. Right, and the cool thing here is, so indexes, we don't have to worry about. Postgres and relational databases do a lot under the hood to make querying and searching for data efficient with indices and something called a B tree, and it uses the tree data structure a lot. And that's all more advanced and not stuff you would probably touch as a dev anyway, unless you start to get more specialized in that world. The foreign key constraint is relevant to us, and it says, and to go back to the question about, well, it looks like there's two ways to define a foreign key. We can just use this shorthand reference, and Postgres does the work for us of saying like, hey, this is a foreign key on another table's primary key. And we can see, hey, this purchases table, it's got a foreign key customer ID and it references the customer ID table. So these commands to describe stuff are really useful, because that lets us confirm that I wrote my SQL correctly and I'm seeing what I expect to. So now I am going to run a little bit of SQL right in Postgres so that we can create some data. So what I've got down here, and I'll bump this up a bit. What I've got down here, if you all can see it, is an insert statement. Insert into the purchases table, and I give the name of each column in parentheses, values, and then again in parentheses, the value that I want to pass to each column. Now, if I run this, I get an error. And the error says, insert or update on the purchases table violates the foreign key constraint. This key, customer ID equals 999, is not present in the customers table. So remember, I talked about relational databases giving us structuring data and data integrity. This is a great example of that. Now that we've defined this foreign key relationship, I can't create a purchase for a customer that doesn't exist. And that is, generally speaking, a good thing. So I just want to pause and see if anyone has any questions before I kind of keep rolling with this. So let's go ahead and create a customer. I just pasted this in. So, and actually, something good to note. Let me type this out actually and clear this. Just a very good note here. So something good to note. About SQL, whether you're writing SQL directly in P-SQL or in an SQL file, is that in P-SQL, hitting enter does nothing. It's that semicolon at the end that tells P-SQL and Postgres, all right, this SQL statement is done, execute it. I can do as many lines as I want. Right? Insert into the customers table for these values, first name, last name, and email. And you can have this in whatever order you want, right? You just want the order of the column names to match up with your data. And now when I add the semicolon, what did I do wrong? I thought that was going to work great, but let's see, insert into customers, first name, last name, email. let's try syntax error at or near insert. Let me just do a sanity check here to make sure I am not doing this totally wrong. No, that syntax looks about right. Let's try this again. Insert into customers. Let me make sure I have that name right. And I will say one of the challenges with SQL is that your error messages are not always very helpful. There we go. So I guess I tried to slice it a little too thin, or I had a typo somewhere. But when that insert statement is successful, you see something like this. The zero, we can ignore. I left a link in the curriculum explaining what it is, but it's some under the hood Postgres thing we don't care about, and it's always going to be zero. The second number matters. This is the number of columns that is created. So whenever you like run a command that creates data or alters data or queries data or deletes data, you should see like it'll tell you the number of columns affected. And now if I do select star from customers, and star stands for give me all fields, I get Alice Waters. I could also do select email from customers. If I just want to see an email, I could also do select ID email from customers, right? So we'll talk about querying later, but for this select statement where we query our data, you can give it the specific columns that you want, or just use star for all columns. And a lot of the times I'll just do star right off the bat just to kind of see what's going on. And I'm going to go ahead and I'm actually going to create another SQL file. Let's call it create mock data.sql. You'll hear this term mock. It's basically fake data or test data. And I am going to do a little copying and pasting here. And let me show you what I copied and pasted. So I've got this customer, Alice, that we already created. I've got another customer named Bob. And now we're creating some purchase data. And the thing to note is this, which column is it here? This first column here. So the first thing to note are insert statements. We never pass the primary key value. Postgres creates that for us, right? I don't have ID here. Postgres will do that for us because we've told it to with that serial primary key on the column. For our purchases table, for this foreign key, these have to be primary keys that actually exist. So I did cheat a little bit here. You have to know for a foreign key, if you're inserting in, you do have to know like what the primary key of like a real row is. And Postgres starts primary keys at 1. So I know that we create 2 customers. So I know that their primary keys will be 1 and 2. And that's pretty common when you're creating sample data or mock data. So I'm going to run this command again. This /i create mock data. That's going to run all these insert statements. And it tells me 3 things happened. 2 insert statements that created 1 row and 1 insert statement that created 2. And I think we have 2 Alices now, which makes sense because we didn't add a unique constraint, say here on the email. So there's nothing stopping us in our data schema right now from having customers with not only the same name, but even worse, the same email. And then this last insert statement. So note that here, I'm inserting two things in one SQL statement. I've got my comma down here, but in this one statement, I'm inserting two things into the purchases table. So for this insert statement, you can insert multiple things. You just have to make sure you know that the column names and the values line up. And so that's why this insert has two at the end, because we've inserted two things. And now let's go ahead and let's look at our data. So let's look at the customers table. And we've got Alice there twice. And this is actually, I deviated a little bit from the lesson. And this is going to screw stuff up because I did mean for the primary key number 2 to connect to Bob, but that's okay. And so this is actually another great example of the importance of constraints and data integrity, because you can imagine how having two users with the same email is really going to screw stuff up in a database. And that's why you'll see there's a unique constraint that you can add. And it's very common to add that to an email address. We don't want, even though this email address is unique, we don't really want to use it as our primary key because it's a string. You can, there are some times when you do that, but it's very nice to just have an integer as a primary key. It's small, it's easy to pass around, it's easy to work with, and a user's email address might change, and that would mess stuff up. So we've got our customer, and we've got, let me rewrite that command from purchases. And we've got our purchases. And note at the end here, the customer ID, I meant for the second one to go to Bob, but I added two Alice's. Alice Waters is a famous chef, and Bob Hope is an entertainer. So that was my thinking there. So yeah, I've covered a lot of ground here. And I just kind of want to pause and check in and see what questions people have. And this is a great time to ask questions. We're going to be spending plenty of time with this. But I wanted to, kind of cover the fundamentals and some of the most important things about Postgres and relational databases right off the bat. How are people feeling? Can I get maybe like a thumbs up or like some sort of middle of the road emoji, like maybe a smiley face that's flat, or I don't know, a cloud, or a thumbs down, depending on how people are feeling about this stuff thus far. Awesome. Michael, is that like a mind blown emoji, or what's the story there?
No, I was just looking through the emojis. I was trying to find one.
Thanks. I'm sorry, there's some noise out there. And Josh, I saw the skull. Is that like you're gonna kill it with SQL, or you're feeling like there's a lot going on here, or what's the story?
Yeah, I'm gonna kill it.
Anything on your mind that you want to go over? Okay, cool. So today I really tried to design today's lesson to focus on the basics. Stuff will get added on top of this. So really today's focus, we'll like designing databases in the second part of our lecture, but getting comfortable with like simple data schemas with like 2 or 3 tables with primary and foreign keys. So we have table relationships, and just using these fields that we've seen here of integer and varchar and primary and foreign keys, really. And then making some basic select statements We're going to talk more about select and querying tomorrow, but you've sort of seen the basic syntax of like select and then the columns we want from a table. There's a little bit more that I want to show, and I'll do that, I think, right now. And then that'll be a good time for a break, and then we can do a little bit of a workshop, I think. There was a bit more I wanted to cover, but I can come back to it later because it's not critical, and maybe I'll save it for the end of the lesson.
Hey,
So
I have a quick question, Adam.
yes, please. What's up, Robert?
I was just thinking about like if we were doing this. So I understand like you create the SQL file here where you're using to create like your database schema. How did you connect this .SQL file to the database again?
Yeah, great question. And actually, I wanted to touch a bit on why I did the SQL files as well. So we can do if we wanted to in P-SQL, you know, we could do like we could create tables just straight up in P-SQL. And let me actually jump up to some of my guide code here for reference for it. Like I could do create table products, ID, serial, primary key, name, varchar. And now I've created a products table. The reason I wanted to demonstrate using SQL files, and I'll show you in a moment. So to answer your question, Robert, P-SQL has a command /i. I don't know what the I is short for, but it lets us execute an SQL file. So, and the thing to imagine here is, imagine we're working at Walmart Labs, and the Postgres database is running on a server in the cloud. P-SQL is running on our laptop, and my SQL file is on my laptop. So with /i, I can tell P-SQL, run this SQL file. Here is the relative path, right? If I was a directory up, I'd have to do that to where it is. You could also do an absolute path if you want, you know, users Adam C code, you know, and so on into like where the file is, but the relative path is just going to be a lot easier. So again, I recommend just like run P-SQL in the same directory that your SQL is in. And then P-SQL will say, all right, I'm going to send this SQL to Postgres, and Postgres will execute it. And now in this case, note that like if you try to create a table that already exists, we get an error that says relation customers already exists, relation purchases already exists. And the reason I think it's useful to write SQL files is first, so you can, I think it's just a little easier in terms of writing. And second, so I can drop table customers, and it's telling me drop cascades. Let's try drop table products. That one should work fine because there's nothing there. So drop is short for delete. Drop table purchases. So now the purchases table and all that data is gone. And note that it didn't let us delete customers first because purchases referenced it. So you can give Postgres rules, it's called cascading, about how to handle delete, but that's another way that relational databases enforce integrity. Drop table customers.
Yeah, it's starting to come back to me now. I appreciate it.
For sure. And so a lot of the times when you're designing a database and working with SQL, if you screw something up, it can be a real pain to fix it. sometimes it's easier to just drop the whole database or all the tables and then rebuild it. And if you have SQL files that are sort of your source of truth and that you keep up to date, then this becomes a lot easier. Like I didn't get to it, but in the lesson for today, I actually show you could create a different SQL file for each table. And there's something to be said for that, because then if I need to get rid of one table and recreate it, I have like one SQL file that I can run. You know, I could do like /I create customers table.sql. I think that's actually a very nice way to organize stuff to keep it separated. It adds a couple extra steps, but it gives you a lot of flexibility. Sort of for demo purposes, I wanted to just have it a little simpler. But so now I can delete the whole database and I can rebuild it in 2 commands with those SQL files. So that's the other reason to write your code in SQL files. It makes it really easy as you're working and debugging. I think the one thing I want to show before we break is an SQL query with a join, and then we'll break. And actually, before I do that, do folks have any questions about sort of what I was just walking through with SQL files, or really anything else that we've covered? Okay, cool. So I think P-SQL is great for helping to design queries. Like, let's say we want to find everything that Alice bought. Well, I know how to get customers, but how do I get Alice? And you all may have seen this where command. Actually, I'll do this in all caps, so it's easier to read. And I'll just do by first name for simplicity, but email would be better because it's a unique identifier. So the where clause of a select statement is how we filter our queries. And if you go online, you can find there's all these like Venn diagrams of like circles and circles that overlap and stuff. You know, but sort of think about like we've got all the customers, and then we just want to filter it for whatever it says in this where clause. And you can do all sorts of things in there, and we'll see that more tomorrow. So the other piece that we need to see is, how do I do a query across tables? And this is where these foreign and primary keys come in. I can do select items from purchases. And by items, of course, I mean item singular. And note that we have this nice hint. The error says column does not exist. It tells us the problem. Perhaps we meant to refer to the column purchases.item. And yes, I did. And I don't need the purchases up front because we've got the table name there and we just need the column name. So I can do that. And I can do, I can filter, and I guess Alice is employee. I can filter by customer ID, but let's pretend that I don't know Alice's ID off the top of my head. And let's say I also want to see her email. So let's do something like this. Select customers.email, comma, purchases.item, join, and I'll write this out in an SQL. And actually, I'll do this in multiple statements here, and I'll put it into the file. So remember, if I don't add the semicolon, SQL doesn't execute this yet. So the join command is how in a query we connect tables together and we use those foreign and primary keys. So we're telling Postgres, I want you to query, I want you to imagine two spreadsheets that we're putting into one big spreadsheet, right? And we dump the stuff from spreadsheet number 1 on the left half and the stuff from spreadsheet number 2 on the right half. But how do we know which rows line up if we were to organize them? Well, that's our primary and foreign key, and we know that they have to match. So if you imagine like an Excel sheet with the customer data and the customer ID and a purchases spreadsheet, excuse me, that has the customer ID, we need to match up those things. And that's what this join statement does. And the join goes after the select, where we tell Postgres what columns we want, but it goes before the where clause where we filter, because we're filtering across all of these tables that we're joining. And the where clause always goes at the end. And it looks like I have a syntax error, which, let's see, at or near. This is always a little irritating. And I don't know if this is maybe Postgres doesn't like me adding this as separate things. So let's actually try running this as a query real quick. If anyone sees my error, please shout it out.
I initially thought it was customers plural .id.
Oh, let's see, oh, you're absolutely right. It is customers plural .id. And note that if I hit the up arrow, it gives me the whole thing, which is great. No, unfortunately not. That would have been nice if that was it. This is also where I think writing it in an SQL file is easier. Because I can see it. There are some VS Code SQL extensions. You can actually connect VS Code to Postgres, and then I think you'll get really good type hints, but I haven't gone that far. So let's see how this works if we get the same error. Yeah, so I'm pretty sure I probably just have a syntax issue going on here. Or I have a typo somewhere else.
You did recreate the table earlier, right? When you were adding and dropping them.
That is a great call. I did indeed recreate the table, and we've got customers and purchases, and we've got select customers email. So my rule of thumb is when something's not working, simplify it. And it looks like it's maybe the join statement. Join table on, oh, maybe, oh, of course. So I think I know the problem. I did join table dot ID. If I look at the Postgres docs, it's you join the name of the table, and on is the two columns that you want to match. So let's try this again. Yeah, in fact, I apologize. I got a number of things wrong here. But if nothing else, it is a good lesson on debugging with Postgres, which can be a bit tricky because yes, it tells me what's going on here, that this join syntax is incorrect. But a lot of the times you need to just refer to like a good example somewhere else to get it working. And that is progress. So this error is much easier to understand. When you start joining and combining tables, Postgres, like if a column name is unique across all the tables, Postgres is fine. But Postgres is like, hey, the customers table has an ID. The purchases table has an ID. I don't know which one this is. So that's what it's complaining about there. And now we have our data. And in fact, if you want to, you can just, as a habit, add the table name for join statements. So that's actually a good error to see. And similarly, like if we want or need to we can add the table names to the columns that we're searching for as well. It's not the worst thing to do because it does make it easy to see like where these things come from, though it does make it a bit more verbose. So I know I jumped a bit ahead here, but just to recap, when we make a query and we want to connect tables, and if I go back, let's review this diagram, right? A customer's primary key is the foreign key on purchases, and that's the connection that we're working with here. When we're querying that data, we use this join statement, and the syntax is select from the first table, join the second table on, and then we give the primary key and the foreign keys that we make the connection and whatever our where clause is. And I think I actually had this right in the lesson. I just was mistyping, which is a bit of a good lesson as well. Oh, and I'm seeing in the chat, Megan, that looks good as well. We're going to talk more about like left joins and right joins and stuff later. For today and for most of the time, just using join is fine. We'll talk more, I believe it's tomorrow or Wednesday, about like the different kinds of joins. By default, if you just use join, I think it's an inner join in Postgres. So why don't we take a break here? Because I know I've been talking for a bit. So why don't we take, what do folks want to do, like 10, 15, and then we can come back for like some workshop stuff? Yeah, let's do 15.